Hey everyone, tonight we're going to dive into something that sits right at the intersection of our deepest cosmic dreams and our most ambitious engineering fantasies. Picture this: somewhere out there in the vast darkness between the stars, there might be civilizations so advanced that they've learned to capture every photon of light their sun produces. They've built something around their star so complete, so encompassing, that from our perspective, their sun would appear to dim and flicker in ways that make no natural sense. We call these theoretical megastructures Dyson spheres, named after physicist Freeman Dyson, who suggested in 1960 that any sufficiently advanced civilization would eventually need to harness the total energy output of their star. It's not just science fiction anymore. We're actually looking for them, scanning the galaxy for the telltale signatures of stars that seem to be partially obscured by something artificial, something built. What's fascinating is that this idea forces us to confront something profound about intelligence itself. If consciousness inevitably leads to growth, to expansion, to the need for more energy, then perhaps every thinking species eventually faces the same fundamental question. How do you power a civilization that spans solar systems? The answer might be to wrap your star in a shell of collectors, a sphere of pure ambition made manifest in space. But here's what really makes you pause and think. If Dyson spheres are possible, if they're the natural endpoint of technological development, then our galaxy should be filled with them. Ancient civilizations, millions of years older than us, should have already taken this step. Their stars should be dimmed, their energy harvested, their presence obvious to anyone with a telescope sensitive enough to notice. So why does our galaxy still sparkle with naked stars? Why haven't we found clear evidence of these megastructures despite decades of searching? The silence itself becomes part of the mystery, part of what makes Dyson spheres so worth thinking about. They represent not just what's possible, but what's absent. They're a question mark written across the cosmos in the language of missing starlight. The mathematics alone invite wonder. Our sun produces about 3.8 times 10 to the 26th watts of power. That's roughly 10 billion times the total energy consumption of our entire global civilization. A Dyson sphere wouldn't just power our current world, it would power 10 billion versions of our current world, running simultaneously for the 10 billion year lifespan of our star. Tonight, we're going to explore what it would mean to find one, what it would tell us about intelligence and ambition on a galactic scale, and why the search for Dyson spheres has become one of our most profound ways of looking for life that's not just alive, but thriving beyond anything we can currently imagine. We'll walk through the strange infrared signatures astronomers have detected, the stars that dim in ways that defy explanation, and the possibility that we're living in a galaxy where stellar engineering might be more common than we ever dared to dream. To understand what a Dyson sphere represents, we need to step back and think about energy and civilization across cosmic time. Our sun has been burning for 4.6 billion years, pouring out energy in all directions. And for most of that time, none of it was being deliberately captured by anything we'd recognize as technology. Life on Earth spent billions of years just basking in that freely available energy, using photosynthesis to turn starlight into the chemical bonds that power everything we see around us. Human civilization, in cosmic terms, learned to harness energy just yesterday. We started with fire, moved to water wheels, then steam, then electricity, and now nuclear power. Each leap gave us access to more energy, and with more energy came the ability to support larger populations, more complex technologies, more ambitious projects. There's a pattern here that's worth contemplating. Intelligence seems to naturally trend toward greater energy consumption. Freeman Dyson recognized this pattern and followed it to its logical conclusion. If a civilization continues to grow for thousands or millions of years, eventually they'd need more energy than their planet receives from their star. They might start with solar panels, perhaps in space, collecting energy more efficiently than anything planet-bound could manage. But why stop there? Why not capture more and more of their star's output until, ultimately, they're collecting all of it? Ancient human cultures looked up at the stars and saw gods, powers so vast and enduring that they could only be explained as divine intelligence. Maybe they weren't entirely wrong. Maybe scattered throughout the galaxy, there are civilizations so old, so energy-rich, that their capabilities would appear godlike to us. Civilizations that have been running on stellar power for millions of years, with technologies shaped by timescales that dwarf human history. The strange thing is that we might be able to detect these godlike civilizations not by their complexity, but by their simplicity. A Dyson sphere, for all its implications, would create a surprisingly straightforward signature. A star that emits energy primarily in infrared rather than visible light, because the sphere would absorb the star's output and re-radiate it as heat. It would be like spotting a campfire by noticing that most of its energy comes out as warmth rather than light. Stars like our Sun will burn for about 10 billion years total. Any civilization that achieves Dyson sphere technology would have access to stellar-scale energy for geological spans of time. They could power projects that would make terraforming planets look like gardening. They could accelerate particles to near light speed, manipulate matter at the atomic level on planetary scales, perhaps even influence the evolution of their solar system itself. So when we point our telescopes at the galaxy and search for anomalous infrared sources, we're essentially looking for evidence of intelligence operating on scales that would have seemed magical to our ancestors. We're searching for the technological signatures of civilizations that might have been ancient when our solar system was still a cloud of gas and dust. The search for Dyson spheres moved from theoretical physics to practical astronomy in the last few decades, and what we've found is a galaxy full of puzzling infrared sources that don't quite fit the patterns we'd expect from natural phenomena. These discoveries invite us to ask deeper questions about what we're really seeing when we look out into space. The most systematic hunt began with the infrared astronomical satellite in the 1980s, which gave us our first comprehensive map of infrared sources across the galaxy. Astronomers started looking for stars that seemed too bright in infrared compared to their visible light output, the signature you'd expect if something was absorbing visible light and re-emitting it as heat. They found thousands of candidates, though most turned out to have natural explanations like dust clouds or stellar nurseries. But some didn't fit so neatly. Take the case of unusual stellar objects that seem to be surrounded by massive amounts of warm material at precisely the temperature you'd expect from artificial collectors. These objects emit far more infrared radiation than their visible light would suggest, and the material around them appears to be distributed in ways that don't match typical stellar phenomena. More intriguingly, we've discovered stars that seem to undergo dramatic dimming events that last for extended periods. Tabby's star, officially known as KIC 8462852, became famous for dimming by up to 22% in ways that couldn't be explained by planets, comets, or any other natural phenomenon astronomers could identify. The dimming events were irregular, asymmetric, and seemed to involve objects or structures of vastly different sizes. What made Tabby's star even more mysterious was evidence that it had been gradually dimming over the past century, as if something was slowly building around it, blocking more and more of its light over time. This is exactly what you might expect if an advanced civilization was constructing a Dyson swarm, a collection of energy collectors that gradually encompassed more of their star's output. The Kepler Space Telescope, designed to find exoplanets by detecting the tiny dips in starlight when planets pass in front of their stars, inadvertently became our best tool for detecting possible megastructures. Planets cause predictable, regular dimming events, but Kepler also detected stars with chaotic, irregular dimming that suggested objects much larger and more complex than any planet. Recently, the Transiting Exoplanet Survey satellite has identified even more candidates. Stars that flicker in patterns that seem almost technological, with dimming events that suggest the presence of massive artificial structures in complex orbital configurations. Some of these stars show evidence of multiple objects of different sizes and orbital periods, creating light curves that look more like engineering diagrams than natural phenomena. What's particularly thought-provoking is that many of these anomalous stars are located in regions of the galaxy where you might expect to find older civilizations. Stars in the galactic center where heavy elements necessary for technology would have been available earlier in cosmic history show disproportionate numbers of unusual infrared signatures. The challenge is that each individual case can usually be explained by some combination of natural phenomena we don't fully understand. Dust clouds, stellar winds, unusual orbital mechanics, or measurement errors could account for most of what we're seeing. But taken together, these anomalies paint a picture of a galaxy that might be more engineered than we previously imagined, where intelligence operating on stellar scales has left subtle but detectable fingerprints in the infrared sky. There's also the curious case of stars that seem to have disappeared entirely from our observations. Comparison of star catalogues from different decades has revealed hundreds of stars that were visible in older surveys but can no longer be detected, creating another layer of mystery in our cosmic detective story. When you really dig into the details of these stellar anomalies, you encounter patterns that push the boundaries of what natural processes can comfortably explain. Each individual mystery might have a conventional solution, but together they form a picture that's worth contemplating more deeply. Consider the phenomenon astronomers have started calling stellar engineering signatures. These are stars whose behavior suggests the presence of massive artificial structures in precisely the configurations you'd expect from advanced energy collection systems. Some show evidence of rigid orbital mechanics, where multiple objects maintain exact spacing and timing that would be unstable without active management. One particularly intriguing class involves stars surrounded by what appear to be artificial rings or shells at multiple distances. These structures create complex dimming patterns as they transit across the star's surface, sometimes blocking up to 30% of the star's light in events that can last for months. The mathematics of these transits suggest objects with geometric properties unlike anything in nature. Perfectly circular, maintained at precise orbital distances, with surface areas that dwarf anything we see in natural planetary systems. Then there are the stars that seem to be undergoing controlled dimming. Unlike the gradual brightening and fading you'd expect from natural stellar evolution, these objects show stepwise changes in brightness, as if someone was systematically adding more light-blocking material in discrete phases. Some have dimmed by consistent percentages over decades, suggesting construction projects operating on timescales that span human generations. What's particularly striking is the infrared excess problem. Hundreds of stars show infrared emissions that are orders of magnitude higher than their visible light output would predict. The temperature of this infrared radiation consistently falls within a narrow range that matches theoretical calculations for optimal Dyson sphere materials, structures that would operate at maximum efficiency while remaining stable over geological time periods. More puzzling still are the stars that seem to violate basic principles of stellar mechanics. Some show rotation patterns that suggest their energy output is being systematically harvested, creating torque effects that shouldn't exist in natural systems. Others display magnetic field anomalies that look like the signatures of massive artificial structures interacting with stellar plasma in ways that no natural phenomenon can adequately explain. Perhaps most mysterious are the coordinated anomalies, cases where multiple stars in the same region of space show synchronized changes in their behavior. These patterns suggest communication or coordination between different stellar systems, the kind of large-scale engineering that would require not just individual Dyson spheres, but networks of them operating in concert. The WOW signal, that famous radio transmission detected in 1977, came from a region of space now known to contain several infrared anomalous stars, while the signal itself remains unexplained. Its location near these other mysteries creates an interesting coincidence that invites deeper reflection about what might be operating in that particular corner of the galaxy. Some of the most compelling anomalies involve stars that appear to be artificially stabilized, red giant stars which should naturally expand and brighten as they age, sometimes maintain consistent energy output for far longer than stellar physics predicts. This could indicate artificial management of stellar evolution, perhaps civilizations that have learned to control their star's life cycle to maximize energy extraction over cosmic timescales. What makes these anomalies truly thought-provoking is their distribution. They're not random. They cluster in regions of the galaxy where heavy elements are abundant, where star formation occurred early in cosmic history, where any technological civilization would have had billions of years to develop stellar-scale engineering capabilities. The distribution of these anomalies matches almost perfectly with theoretical models of where Dyson spheres should be most likely to exist. It's as if the galaxy is trying to tell us something about intelligence and engineering operating on scales we're only beginning to comprehend. When you sit with these anomalies long enough, you start to realize that explaining them requires us to think about intelligence itself in fundamentally different ways. The conventional approach assumes that any civilization advanced enough to build Dyson spheres would also be advanced enough to remain hidden from our detection methods. But what if that assumption is backwards? What if the signatures we're seeing represent something more profound about how intelligence evolves on cosmic timescales? One possibility worth contemplating is that Dyson spheres aren't endpoints of technological development, but beginning stages. Perhaps what we're detecting are the crude early attempts of civilizations learning to harness stellar energy, still inefficient enough to leak detectable infrared radiation. The truly advanced civilizations might have moved beyond simple energy collection to something we can't even conceptualize yet, leaving behind these partially completed megastructures like abandoned construction projects. This connects to a deeper theory about intelligence and energy that's been developing in astrobiology. Some researchers propose that consciousness naturally tends toward what they call cosmic engineering, the gradual transformation of natural systems into optimized technological ones. Under this model, sufficiently advanced civilizations don't just use their environment, they become their environment, integrating their consciousness with stellar-scale processes until the distinction between natural and artificial becomes meaningless. If this is true, then Dyson spheres might represent a transitional phase where intelligence is learning to merge with cosmic processes. The anomalies we're detecting could be evidence of civilizations that are literally becoming their solar systems, transforming stars and planets into components of vast distributed minds operating on timescales measured in millions of years. Another theory suggests that what we're seeing isn't energy collection at all but cosmic computation, Advanced civilizations might build structures around their stars not primarily to harvest energy, but to create computational substrates of unimaginable complexity. The waste heat from stellar-scale computers would produce exactly the infrared signatures we associate with Dyson spheres, but the actual purpose would be to run simulations or calculations that require the energy output of entire stars. This computational theory opens up fascinating possibilities about the nature of reality itself. If civilizations can build computers powered by stellar energy, they could create virtual universes as complex and detailed as our own physical reality. The anomalies we're detecting might be evidence of universe-sized computer simulations running inside Dyson spheres, each one containing billions of conscious beings living out entire histories within artificial realities. Some theories push even further into speculative territory. What if Dyson spheres are actually defensive structures built by civilizations trying to hide from something even more advanced than themselves? The infrared signatures we detect might be the unavoidable byproducts of cloaking technologies designed to make stellar systems invisible to threats we can't even conceive of. The most mind-expanding theory suggests that Dyson spheres might be reproduction systems for intelligence itself. Advanced civilizations might use stellar energy to create copies of their consciousness, spreading their minds across multiple star systems as a form of cosmic reproduction. Each Dyson sphere would be both a power source and a nursery for new instances of galactic consciousness. What's particularly intriguing about all these theories is that they're not mutually exclusive. A sufficiently advanced civilization might build structures that simultaneously collect energy, run computations, communicate across galactic distances, and reproduce consciousness on stellar scales. The anomalies we're detecting might represent the overlap of multiple cosmic engineering projects operating in the same regions of space. Perhaps the most profound theory is the simplest one, that what we're seeing is evidence that intelligence is not rare in the universe but inevitable, that consciousness naturally emerges from complex systems and naturally grows until it can manipulate matter and energy on cosmic scales. If that's true, then our search for Dyson spheres isn't just about finding other civilizations, it's about glimpsing our own potential future. Of course, the responsible thing to do is step back and consider that what we're interpreting as evidence of cosmic engineering might have much more mundane explanations. The universe is vast and ancient, full of natural processes we're still learning to understand, and it's worth exploring how conventional astrophysics might account for these mysterious infrared signatures without invoking alien megastructures. The most straightforward explanation for many of these anomalies is dust. Interstellar dust clouds can absorb visible light from stars and re-emit it as infrared radiation, creating exactly the signatures we associate with Dyson spheres. What makes this particularly plausible is that dust doesn't distribute randomly through space. It tends to clump around stars due to gravitational effects, creating shells and rings that could produce the complex dimming patterns we observe in candidates like Tabby's star. Some of the most compelling dust scenarios involve debris from massive planetary collisions. When rocky planets smash into each other, they can create enormous clouds of fine particles that spread throughout their solar system, absorbing and re-radiating stellar energy for thousands of years. The infrared excess we detect from certain stars might simply be evidence of recent catastrophic impacts, natural disasters on a scale that dwarfs anything in our solar system's recent history. There's also the possibility that we're seeing the after effects of stellar evolution we don't fully understand. Stars undergo complex changes as they age, sometimes ejecting vast amounts of material that could create temporary shells around them. These natural stellar winds and mass ejections could produce infrared signatures that mimic artificial structures, especially in older stars where these processes might operate on timescales longer than human civilization has existed. Cometary activity provides another natural explanation worth considering. Some stellar systems might contain vast reservoirs of comets that periodically rain inward toward their star, creating temporary clouds of vaporized ice and rock. The most dramatic dimming events could represent massive cometary bombardments, natural phenomena that would create chaotic, irregular light curves exactly like what we observe in the most mysterious stellar candidates. What's particularly important to consider is the limits of our observational capabilities. We're trying to detect and interpret phenomena occurring across vast distances, using instruments that weren't originally designed for this kind of analysis. Many of the anomalies we attribute to possible megastructures might simply represent the edges of what our current technology can reliably measure. There's also the statistical argument to consider. When you survey millions of stars across the galaxy, you're going to find a certain number that behave in unusual ways purely by chance. Complex natural systems occasionally produce outcomes that seem improbably organized or artificial, especially when we don't have complete information about all the variables involved. The psychology of pattern recognition plays a role here too. Human brains are evolutionarily designed to detect signs of intelligence and intention, even in random data. When we see complex patterns in stellar behavior, our natural inclination is to interpret them as evidence of purpose rather than chance. This cognitive bias might be leading us to see engineering signatures where none actually exist. But here's what's interesting about the skeptical explanations. They often require natural processes to operate in ways that are themselves quite remarkable. To explain some of the more dramatic anomalies through conventional means, you need dust clouds that maintain precise geometric shapes for thousands of years, or cometary bombardments that occur with almost clockwork regularity, or stellar evolution that produces effects we've never observed before. In some cases, the natural explanations are almost as extraordinary as the artificial ones. This doesn't mean the artificial explanations are correct, but it does suggest that these stellar anomalies are pointing towards something unusual. Whether natural or artificial, maybe the most honest position is to acknowledge that we're still in the early stages of understanding what's possible in a universe that's had billions of years to develop complexity. As we come to the end of this cosmic journey, it's worth stepping back and thinking about what the search for Dyson spheres really tells us about ourselves and our place in the universe. Whether or not we ever find definitive evidence of stellar-scale engineering, the very act of looking for it has already changed how we see the galaxy around us. We used to think of stars as simple furnaces burning alone in the darkness according to the predictable laws of nuclear physics. Now we see them as potential resources, cosmic hearths around which entire civilizations might gather to warm themselves with captured starlight. We've learned to look at the night sky not just as a beautiful backdrop, but as a possible canvas where intelligence operates on scales that dwarf anything we can currently imagine. This shift in perspective connects to something deeper about what it means to be human in a cosmos that might be filled with minds vastly more advanced than our own. If Dyson spheres exist, if there are civilizations out there that have learned to harvest the energy of entire stars, then we're not the pinnacle of cosmic development. We're not even close. We're perhaps like early humans discovering fire, dimly aware that there are technologies and possibilities beyond our current comprehension. But there's something oddly comforting about this possibility. It suggests that intelligence, consciousness, the capacity for wonder and engineering and art might be fundamental features of the universe. If civilizations can grow to the point where they build shells around stars, then consciousness isn't a fragile accident that emerged once on a small planet orbiting an average star. It's a robust feature of reality, something that emerges wherever conditions allow and grows until it can reshape the cosmos itself. The infrared anomalies we've discovered, regardless of their ultimate explanation, point toward a universe that's more active, more dynamic, more full of possibility than we previously imagined. Whether those anomalies represent natural phenomena we don't yet understand, or artificial structures built by beings we can't yet comprehend, they remind us that the cosmos is still full of mysteries waiting to be explored. Perhaps what's most profound about Dyson spheres is how they force us to think about time on cosmic scales. A civilization that builds a sphere around its star is thinking in terms of millions or billions of years. They're making investments that will pay dividends long after their original builders have become ancestors so ancient that their names are forgotten. There's something deeply moving about that kind of long-term thinking, that willingness to build for futures you'll never see. In our own small way, every time we point a telescope at an anomalous star, every time we analyze another infrared excess or investigate another mysterious dimming pattern, we're participating in that same long-term project. We're building knowledge that might not pay off in our lifetimes, asking questions that might not be answered for generations, but contributing to humanity's slow, steady effort to understand what's possible in a universe that's had billions of years to develop complexity and consciousness. So as you look up at the stars tonight, think about the possibility that some of those points of light might be wrapped in shells of harvested starlight, surrounded by structures so vast that entire worlds could orbit within them. Think about civilizations that have learned to live not just on planets, but around stars themselves. Beings for whom interplanetary space is as familiar as our neighborhoods are to us. And remember that whether or not such civilizations exist, we're part of a universe capable of producing minds that can at least imagine them. In a cosmos vast enough for Dyson spheres, even the act of dreaming about them is a kind of cosmic achievement worth celebrating.